Okay, so we're going to talk about classification, and this first lecture is going to be on classification, is going to be about generative methods for classification. And generally these have sort of fallen out of favor with respect to when we compare to discriminative methods, but generative methods are still very instructive to consider just because they are a good window to see what's at stake when we're talking about classification in the classification setting. Okay, so the Bayes rule in classification states the following thing, and if you're taking my class, then you've seen this from homework. You can recall that the Bayes rule is the following. It just says, let's predict a 1 if the probability of y equals 1 conditional on x exceeds the probability of y equals 0 conditional on x. So this is the Bayes rule for the 0-1 loss. And another way to write this event is if you have f of y and x, that's the density of the joint density of y and x, y equaling 1 and x, that this exceeds the joint density of y and x, where y is equal to 0. So that's another way to write this event. And the only difference between these two is we multiply both of these sides by the marginal density of x. So if we let pi equal to the probability, the marginal probability of y equaling 1, then we can also, using Bayes rule, or just the definition of the conditional density, we have that that this joint distribution can be written as the conditional of x given y times the marginal of y, and that's pi times f sub x given y, right? X conditional on 1, and that's this left-hand side of this joint distribution. And then we have the right-hand side of the joint distribution, but now instead of probability y equals 1, we have probability that y equals 0, which is 1 minus pi. So this is now another expression for the Bayes rule. And then when we write this out, we get that f sub x given y of x conditional on 1 over f of x given y, x conditional on 0. This exceeding this tau, where tau is equal to 1 minus pi over pi. This is like the odds ratio of 0 versus 1. That this is another expression for the Bayes rule. Now the things that we needed for this are the density of the 1s, the density of the 0s. So if we condition on y equaling 1 and condition on y equaling 0, this is the density of all of the x's such that y is 1. And this is the density of all the x's such that y is 0. And then we're just asking, is this ratio of the densities exceeding tau? And this should be familiar for anyone who has done hypothesis testing. If we call one of these the alternative hypothesis, say the y equals 1, and the other the null hypothesis, y equals 0, then this looks like a likelihood ratio test. We're asking, does it come from the density? Does the x come from the density under the alternative hypothesis or the null hypothesis? We take the likelihood ratio here and threshold it. So this is equivalent to a likelihood ratio test, and we're testing whether y is going to be 1 or 0 for a new point. Of course, the issue with the Bayes rule in classification is that it requires unknown information. Typically, we don't know what the joint density of x and y is, and this is unlike simple versus simple hypothesis testing, where we assume that we know what the densities are for the two hypotheses. So what do we do about this? Well, one way to do it, so this is a video, or this is an image of just expressing that point. And on one, what you can imagine is that there are two densities, f0 and f1, which are the conditional densities given 1 and the conditional density given 0. And then we're just going to look at the likelihood ratio of these and then just predict one when the likelihood ratio exceeds the value, and 0 when it is below a certain value. Okay, so generative methods, the basic idea is that we're going to do this very explicitly. We're just going to try to estimate these densities of x given y, and then just plug this into the Bayes rule. So this is a plug-in estimator. So there's two basic ways to do this. One is through non-parametric methods, and typically we use naivebayes to do this. And the other are parametric estimators, where we actually try to get a parametric fit to the density of x given y. The attractive thing about this is that we can just think of x given y as different data sets for the different values of y. So for each label, we just separate out the different data sets, treat them independently, compute these density estimates, and then combine them. So that's one of the attractive things about these types of methods. So to get to this, we have to think about density estimation. Now we've sort of reduced our problem because we're going to use a plugin for the Bayes rule. We reduce the problem to a problem of density estimation. So how do we do density estimation? One is through parametric methods, and we'll talk about that in a little bit. The second way is through non-parametric methods, and we're actually going to start with that. We're going to lead with the non-parametric estimates. There's others, like nearest neighbor methods. Well, a reasonable heuristic for estimating the density f hat x based on some data is to do the following, and this is going to lead into kernel density estimation. So let's just suppose that we're looking at a given point. We're interested in density at a given point. Let's just draw a ball of size epsilon around that point, and let's call that ball n sub x epsilon. And this is just the number of data points within epsilon of x. That's this ball in whatever our norm is. Usually it's Euclidean norm. So we have some number of points within this ball of radius epsilon around x, and then let's just divide out by n times the volume of that ball. And then what we get by we know that the expectation of this n of x epsilon over little n, the total number of points. So we have a data set, and we're dividing. This is just the ratio of the number of points that fall within the ball divided by the total number of points. We know that that's equal to the expectation of that is equal to the probability that one of the data points, if they're IID, one of the data points falls within the ball. But that's going to be very close to, I'm just going to wave my hands and argue that that's going to be very close to f sub x of x times the volume of the ball. This actually gets at the Lebesgue differentiation theorem. So this is actually a very deep concept, but we're just going to say that this is very close to this density times the volume. And so with this approximation and the law of large numbers at hand, we know that as little n goes to infinity, we know that this f hat of x is going to get close to this f sub x of x if this epsilon is also getting small with the number of data points. So this heuristic, let's make it a little more concrete. That total number of points, we can express it through a kernel, which we're going to call the boxcar kernel. The kernel is just a function which says if x0 and x1 are within their distance is less than or equal to 1, the Euclidean distance is less than or equal to 1, then it evaluates to 1 divided by the volume of the ball of radius 1. And so this k is just some function of the distance between x0 and x1 for any two arbitrary points x0 and x1. Then we can re-express the number of points that are within epsilon of x as the volume of this ball of radius 1. So we're just multiplying back out the volume of this ball of radius 1 times the sum over I, this k of the of the absolute value between x minus xi, so this, sorry, the Euclidean norm between x and xi divided by epsilon. So this is just going to evaluate to 1 when these 2 points are within epsilon of one another. That's what this inner part, and then because we sum over I of these, we're going to get all of the total number of points that are within epsilon of x. So our density estimate is going to be, can be written as 1 over n times the sum over I, the volume of B1 divided by the volume of B epsilon times this k of this kernel function of this Euclidean norm, right? And this is just a re-expression of what we had before, which is our estimate is going to be this n x epsilon divided by n times the volume of the ball of radius epsilon. So this is just a re-expression of this density estimate, but written in terms of this kernel function. Now the difference, the ratio of these two volumes turns out to be 1 over epsilon to the p for Euclidean norm. Right? So if you take a ball and shrink it to radius epsilon, then the ratio of the volume changes by, or the ratio of these volumes is epsilon to the p, 1 over epsilon to the p. So, so this is what this is equal to. And now we're just going to use this as a generic formula for constructing density estimates, and we'll call it the kernel density estimator. So we did this using just the boxcar kernelized motivation, but we can generalize this to other kernel functions. Now there was one special property of this boxcar kernel that we really like, and that's that it integrates to 1. So now we're going to say any kernel that we can use for kernel density estimate, it just has to satisfy the property that it integrates to 1, and typically we make it positive as well. So the boxcar kernel, we can see that that's true because when you integrate this indicator, then that's going to evaluate to, the indicator evaluates to 1 over the ball of radius 1 around x1 here. And so its integral, the integral of the numerator here is just the volume of B1, so those two cancel out and gives you 1. In general, our kernel density estimation, our kernel density estimator then, is going to just be this following expression, where all we said is that instead of the boxcar kernel, this can be any kernel that satisfies this property. And P in this case is the dimensionality of the X space. So how your kernel density estimate responds to the dimensionality is through this 1 over epsilon to the P. If P is larger, then you're going to have a larger effect. In this epsilon, we call it a bandwidth parameter. So typically it's sort of expressing how local you want your estimate to be. If it's large, then you're using points that are very far away from your current X prime to give your density estimate. So what does this typically look like? So on the left-hand side, we have an example of a histogram. And on the right-hand side, you can imagine that if you have a kernel centered around every data point, then what you end up doing is you add up all of those kernels for a given point. So maybe our point is right around here. There's a lot of points around it. So there's a lot of kernels that have high value. A lot of these kernels centered around the data points that have some high value around this point that we're considering. And then when you take its sum and then divide out by n, you get a pretty large density function. Right? So these are the kernels divided by n. And then you get a pretty high density function because you sum up all of those different kernels divided by n. But if you're at a point that's very far from all the other points, all of the kernels are very close to 0 or nearly 0. And so when you sum them up, these divided by n, you get a total density estimate that's actually quite small. So this is the resulting kernel density estimator from this example. So finally, this leads to the naive Bayes estimator. So let's bring it back to the classification context. So the basic idea behind our classifier is that for each of our labels, is that for each of our labels, y, and in this case we're going to consider binary classification. For each of our labels being 0 and 1, we're going to let x1 to xny be a predictor, be the predictor data just for a given label, right? So we're going to split our data into the 0s and the 1s, and then each of them we're going to construct a density estimator, but the way we're going to do that is very specific. We're just going to look at each dimension separately. So we have x1j is the jth dimension for the first data point within the say zeros, for example, and then we have up to the jth dimension of the last 0. Right? So we just treat that as if it's our data, and it's univariate data. So we're going to construct a univariate kernel density estimator using our favorite kernel. And we have chosen a bandwidth somehow as well. And then we we're going to construct a total density estimate just by taking the product of all the density estimates for all the coordinates for each dimension. Right, so for every new x prime is a p-dimensional object, we're just going to look at each coordinate of x prime and get an f hat for each of those coordinates by computing the univariate KDE, kernel density estimate, and then just taking the product of all those f hats. Okay, so then now we have densities for all of the labels. Right? So for a new x prime, for example, we have a density for the 0s and a density for the 1s. If we let pi be the proportion of y equals 1s, now we have a pretty good estimate of the marginal probability that y is equal to 1, and we can calculate that tau from before. Now we can predict y hat equals 1 for some new x prime if our estimated density ratio exceeds tau and 0 otherwise. So this is our naive Bayes estimate, and they call it naive Bayes because it's working on each of these dimensions separately. So it's sort of treating them as if it's independent. And if you think about this factorization, that is assuming independence of each of the coordinates, conditional on y. So this is sort of what naive Bayes looks like. This is from MathWorks, this image. The basic idea is that at each point, so these are level sets of your density, at each point you have a density estimate for each coordinate for a given label. So this is a data set with 3 labels instead of just 2. So it's not binary classification, but classification with three different labels. And so for a given label, we just focus on, say, the Virginica label, and then we focus on one of the dimensions, let's say petal length, and then we compute our density estimate. So maybe it's highest here, and maybe it tapers off as we get further away from the data, from the blue data. But it's going to be very low here, whereas for the red, for the Setosa label, we're going to have a very high density for this petal length. And similarly for petal width, we would compute the kernel density estimate for petal width, and then we would multiply those two to get an overall density. And then we would just say, well, if we want to decide between Setosa and Virginica, we would just compute the corresponding density ratio. In general, we would have to, there are multi-class generalizations of this, but we would have to consider a more than one tau in that case. We'll go over that later. So this leads us to our first exercise, which is just meant to reinforce some of the things that we talked about with multivariate density estimation. So first of all, I'd just like to ask a very simple question. Suppose I gave you a kernel instead of the boxcar kernel. It looked like the following thing. So we have x0 and x1 are both in RP, And it looked like the following. It's 1 over 2 pi to the k over 2, the exponential of minus 1/2 times the Euclidean distance squared between x0 and x1. How do we know that this is a valid kernel for multivariate density estimation? So that's the first question. And the answer should be pretty straightforward. You shouldn't have to do much if any calculation to answer it. And then suppose that you use this kernel to obtain a multivariate density estimate. Let's just call it f hat. So that means that you use the multivariate density estimate just based on the formula that we saw before to construct this f hat. And then instead, suppose that you use the subroutine in naivebayes to estimate f hat sub n. So just imagine that we lumped all the data together. We don't have different labels. We just have all of the data in one place. And then you use the subroutine in naivebayes, which means that you estimate each of these coordinates f hat j separately. Right? And then you take their product to get your f hat sub n. Right? Will these return the same result? And try to provide evidence for or against whether they would return the same result. And one instructive thing to think about is instead of this type of kernel, think about the boxcar kernel with bandwidth 1, and just situations in which those two answers may differ, may be the same. So what are the main differences between the methods in that particular case?